Hi everyone, my name is Victor, and today I'm going to use natural language processing to help decode the quantum computing landscape. There's a lot going on in terms of research papers, patents, so on and so forth. And oftentimes, if you take 100,000 of them, 200,000 of them, or even 300,000 of them, it's not the easiest to understand what is going on, especially if you have to come from a sort of high-level overview of where trends are heading, where companies are heading, and what your competition is doing. So today we're going to take a sort of big data analytics approach, where we're going to take as many patents as we possibly can, sample them down, and kind of visualize it for you to see where things are headed in 2023 and where the industry is in general. And at the same time, of course, we want to supplement that with research papers, right, to kind of see where that is headed as well. And last but not least, because we're at a conference, we want to do a quick network analysis as well to show you kind of where the sort of connections are and where that lies in terms of investments. As after all, this is a sort of business and analytics conference. So, part of the conference. So my background is in AI. I'm sort of concentrated in natural language processing. So bear with me here. I'm sure all of you are bigger experts than me in quantum computing, but I'm going to do my best to analyze this sort of landscape for you. So a little bit about the company. We're VALUENEX. We've been around for over 15 years. And so we're not really your sort of stereotypical AI dorm room startup that you might have been hearing about these days. And part of it is also with Japanese culture is to have attention to detail. So when it comes to something like patents, we want to not only just take the title and the abstract, we really want to take the entirety of the patent and weigh the different sections itself so we can provide as accurate of a landscape analysis as possible. And so in Japan, we work with over 50% of Fortune 500 companies. And so in the last few years, we've been based out of Palo Alto and helping out over here as well. This is the sort of bread and butter. Sorry, the lighting isn't great to see everything in detail, but I'll sort of narrate what's going on here. So it's a topological cluster map, and what you have are major areas, which are dense areas. So a sort of collected group of patents in there that suggests everybody is sort of filing patents in the same area, for example. Growing areas, I think that's relatively intuitive. What that is just sort of a density growing much faster relative to everything else over time. You have trend lines and you have centers of distribution of gravity, but I think something more interesting to us is sparse areas. So these are low density areas with high density surrounding it, and oftentimes it's converging towards a lower density area, and that possibly and most likely means an area of opportunity. With that being said, so again, just quickly, I'm going to go through a network analysis, then a patent analysis, and last but not least, a research paper analysis. So starting off with the network analysis, I think part of understanding being at a conference is who you can really talk to, right? And oftentimes, when you take a step back out of the conference, it's who you can work with in terms of strategic partnerships, collaborations, so on and so forth. And even if you did a random walk of 25,000 steps, at the end of the day, you're still going to have these sparse areas where you miss out on people that you could have potentially talked to or partner with that you might not have come across too well. So just to kick things off, it's a short question of where am I? What does the key players in the landscape in quantum computing look like? How can I navigate the network of key players? And so what we have here is a data set of roughly 1,287 companies, founders, and investors that we've mapped out as a beginning to sort of introduce you guys to these graphic network graphs. And what we have is that we show points of centrality and who the key players are, and at the same time, how can you expand your network through a sort of series of walking through different founders or investors or people that can make introductions. At the same time, offline, because this is just going to be a snapshot, we would love to do a live demo, but sort of offline, we'd be able to tell you kind of a temporal analysis as well. How has the network grown over time? How have the investors grown over time? And that can give you an investor analysis, profile analysis as well, as in what are the interests in particular subsets of quantum computing that this investor has been invested in. And last but not least, of course, there's a geographic breakdown too, which I'll show you in a second, but of course we can go into more detail in an interactive manner if you come find me offline. Roughly speaking, this is the key player landscape for quantum computing. And there's a very clear inner circle and outer circle. So again, there's 1,287 companies that include founders, investors, and the key players, a certain subset group of them are concentrated towards the middle. Now, it's not to say that the players on the outside aren't important. They're just equally as important, but it just seems that one group has found themselves to be connected with each other to a sort of higher degree, and that is showcased right in the middle over here. And so if you're there, you feel free to help those that are on the outside come into the inside as well. And to kind of dive a step deeper into who some of these players are, two of the sort of biggest nodes in the middle that connect a lot of things. One is Creative Destruction Lab, and the other is European Innovation Council. And I'm sure these are very familiar names. At the same time, we have the US Department of Energy, National Science Foundation, and we have a lot of familiar faces, some of them with us in Palo Alto, Alumni Ventures, Sequoia, and DCVC. And roughly speaking, that's what consists of the inside sort of group of things. And the sort of ties between each node come in the sense of investments, or if a founder has been part of a different startup that showcases itself across these nodes. I think something much more interesting is the geographic breakdown. So there's a very clear divide when it comes to US, Canada, Singapore, Israel, UK, and then EU you have on the other side. And there's a sort of ridge that comes down the middle that has, according to our analysis, has not been sufficiently bridged. And part of what that means is that, look, if, let's say, Creative Destruction Lab and European Innovation Council can come together to discuss some form of collaboration with their networks, this can be something that expands into maybe even joint funding initiatives or so on and so forth. But of course, I don't know a lot of the stories and politics behind what's here. I'm providing a big data analytics approach to the story that's being told. At the same time, because we're a Japanese company, we kind of want to touch quickly on the Japanese landscape as well. And we have two decentralized spheres up here, circled in red on the top and the bottom. And so looking at the sort of top sphere, what you have here are a distinct set of companies, Q2B23 and Preferred Networks, and Mitsubishi UFJ Capital is the sort of investor that ties everything together. And on the other side, it could be that these companies are sort of more specialized in a certain application, such as aerospace. There's a couple aerospace players here. But as a result, they're sort of separated from the top group and the bottom group. And so even within the Japanese quantum computing landscape, you have these two very distinct groups going on here. So to keep this short, network analysis I think is super useful, and I thought it was quite relevant to the conference, but it's just to get everybody understanding the network graphs and how they work. And let's move on to something much more interesting, which is the patent analysis. So as you know, patents do have a small bit of delay. Well, I guess it jumped forward. It's OK. There's roughly about 4,196 patents that we have established over this space. And the PowerPoint flew all the way forward. I was supposed to walk through each one of them in its own. But as you can see, we have a very big sort of space over here where you are looking at the superconducting sort of circle on the right in red. Sorry, it's not the brightest. I'll circulate the PowerPoint afterwards. And within the superconducting cluster, the red areas are the areas of high density in terms of patents that are being filed. And so what you see is you see superconducting circuit fabrication on the right, electrodes. Then you also see resonators, qubit coupling techniques, and last but not least, quantum processing units. And that roughly gives you that sort of concentrated cluster in the middle that we can generalize as superconducting. And on top of that, you have ion traps. And below that here, in the sort of bottom right, you have topological qubits. It's clearly less dense than the sort of area above, and we kind of know the big player that is the sort of the loudest in that area as well. And quantum dots towards the sort of inner side as well. Right where from my perspective, the light is kind of shining through on the screen, is a ridge that kind of separates the right half to the left half. I'll give you a deeper analysis as to what that is. But on the left side of things, what you really see here is you have quantum annealing, quantum error correction, magic state distillation, quantum analog processing units. You have quantum noise reduction and approximation. You have hybrid quantum systems, and you have quantum circuit generation and design. And those kind of form that second part of the big general cluster over there with a couple red dots highlighted. The purple stuff, you might have noticed, are highlighting some of the sort of less dense areas. And what they are sort of applications. So simulation, you have quantum optimization algorithms, and you have machine learning models and algorithms. And these are just some of the hot topics for this year as well. And so going back to the gap in the middle, sort of between this kind of general hardware side and the software and application side on the left. I think what that really means is that because I'll show you where 2023, how it took a great leap towards the left side. What that means is it moves so fast in terms of patents filed that it really stretched the radar all the way through. And that opened up a lot of blank spaces, or we like to call sparse areas, that are voids that can be filled. And oftentimes that means that maybe research hasn't caught up with it yet, or that, that this is a sparse area that indicates a developmental stage where patents have not been filed yet. And so hence why we believe that there are certain areas of opportunity. And later on, I'm going to filter by 2023 only, and you can see that a lot of the companies are actually pulling back in terms of patents to file and filing somewhere down the middle. So moving on to a sort of better, sorry, perfect. Moving forward a little bit, this is the sort of general story that I'm trying to tell here. The black line is not the most obvious, but what it does is it stretches from 2010 to 2023. And on the right, we have hardware. On the left, we have software. And on the very left side, we have, very right side for you guys, left side for you guys is the application side of things. And then that sort of white box highlights that general ridge where there's a lot of sparse areas and areas of opportunity. So moving by different players, I'm going to go through some of the bigger players, and this further showcases our capabilities of analyzing the industry. So we have a couple bigger players here, and I'd like to show you some differences in terms of the patents that they filed. So right here we have IBM, and as you know, IBM has a very general coverage of most of the entire space, but especially they've been focusing on generation and compilation of quantum circuits, and at the same time, of course, they have a very strong presence in quantum circuit generation, calibration operation, and superconducting technologies. And to contrast that really quickly, you have Google over here, who you see their significant efforts in superconducting circuit fabrication and flux qubits, and you also see some clusters around qubit calibration. And this kind of shows that they're really going for high precision and fidelity at the same time. What we have next is Microsoft. So as you would have noticed down there with topological qubits, this is sort of Microsoft's unique interest. And at the same time, they've spread themselves across the quantum circuit generation and design. But as you notice, there's quite a significant sparse area, at least in terms of the patents that they file, in terms of hardware technologies and software technologies in the application layer. And it's less of a general coverage as the other two. And moving on to D-Wave, and going really quickly through them, is that basically it shows that there's a lot of work being done on quantum annealing and other extension into other superconducting technologies. And last but not least, when you throw everybody together, you kind of get this pie chart of patents that were filed across the board between these major players, and you can see that IBM is leading in terms of number of patents filed, followed by D-Wave, Microsoft, and Google. And you can kind of tell by these little mini almost pie charts as to who has filed the most patents in those areas. And so yes, please come find me afterwards. I can show you the live version, and you can even put your own company there and see how your coverage is doing. And so last but not least, for the patent analysis, we have the 2023 patents. As I said, it's very heavy on the software algorithm side of things, moving into application. But as you can see, companies are starting to fill out that middle ridge between hardware and software. And I think the more development that's needed, and I think this tells you a general story of the entire landscape where hardware has moved into software and application, especially in 2023. And it's stretched so fast that it's opened up all these voids that I think are worth exploring in terms of how you can fill them, and they could be potential areas of opportunity. Of course, at the same time, patents don't tell the most complete story, and there's definitely a time lag in terms of how patents move forward and give you a deeper sort of understanding of what's going on. So it only makes sense for us to kind of move into research paper analysis as well. All right, so on the left here, we have the quantum dot spintronics and semiconductor-based quantum computing as a general major area. And then we have ion trap quantum computing and phonon-mediated entanglement, so on and so forth. And it kind of maps with the patent story as well, where this sort of left general side in the bottom is more hardware related. So I'm not going to go through each one of them, and love for you to come find me afterwards. But of course, there's like topological quantum computation. There's and it moves towards into the middle. You see stuff like quantum error correction techniques. Sorry, I don't have the most visibility of the screen over there. And then sort of on the bottom right side, you have the secure quantum cloud computing and client server protocols, which are a less dense area, but it's definitely something that's growing very fast as well. And then here we have the growing areas, and they're all towards the right-hand side. And I'm going to go into more detail on them in a second, if this clicker lets me get through as many of them as possible. And essentially, sorry, need some help. All right, there we go. So on the top right-hand side, you have the sort of growing areas. And just to highlight a few of them, they're more sort of on the software side of the story. You have sort of the error mitigation techniques in quantum systems. You have quantum simulation, optimization, and Hamiltonian dynamic analysis. You have stuff super, super hot this year as well. You have the quantum machine learning and kernel methods. And then you have other quantum optimization and combinatorial problem-solving techniques. And then again, as I said, because it stretches so fast over, and I'll show you in a second the growing areas and how they stretch, it has opened up a lot of sparse areas in the middle, which are potential voids to fill as well. And some of that we'll go into a bit more detail later. So the black line there is the stretch. The leap is halfway around the black line all the way up to 2023. So in that 1 year, this map just moved all the way into these sort of green areas. And to be honest, of all the maps that I've created, this is one where I have where a significant number of them have become growing areas, especially in the last year. So I think, with that focus being said, that puts us in a situation where we have these sparse areas that are huge. And so some of these sparse areas include spin-bath decoherence, quantum dynamics in noisy environments, and then you also have quantum Monte Carlo methods and sign problem in quantum simulation, and last but not least, you have quantum walks and network entanglement. And of course, these are topics that natural language processing gives in terms of a summarization of what the general area is. It only makes a lot of sense to dive into it in complete detail and kind of go bit by bit and space by space to really dig into what are the specific research papers that are being filed there and what are some other areas of opportunities that are not covered as much that we can take a deeper dive into. So coming back to some of the major areas, they're all the way on the left, as I said before. And I wanted to show something as well where, right after, if you have a couple professors in mind, which I'm a big fan of Dirk England in MIT and Mikhail Lukin at Harvard, you can isolate them on the map in terms of the specifics of who you want to isolate for. So in this case, if you're a company as well, and you filed a couple of research papers or patents, you can take that and showcase it in a sense of isolating it and highlighting it relative to the entire map. So with that being said, I know that there isn't a lot of time to dive into a lot of detail. I'd love if everybody has the time to come find me. I can pull up the sort of interactive radar for you to play with, and that includes the patents, the research papers, and if there's a topic of interest, you're definitely more of an expert than I am. We can go zoom in on a specific section, and we can look at which one's been filed lately, which ones have been slowly being filed through, or which ones are areas of opportunity that you want to consider. And if you are a company that files patents, or if you're an investor who has an investment portfolio, and you want to bring the sort of patents or the research papers of the companies you've invested in, or and you want to sort of showcase your coverage relative to the entire industry landscape, come find us as well. We can just filter by the patents that have been filed by those companies or the research papers that have been filed by those companies, and we can tell you what your general coverage is if you hit all the growing areas, the sparse areas, or the major areas. So that's it. This is us, VALUENEX. This is a sort of core product that we provide, and hopefully it gives you a snapshot of what's happened this year and gives you a snapshot of the quantum computing industry in general. And I'm not sure if I have time for questions, but as I said, if you come find me offline, we can go over this sort of patent analysis in detail, and I'm very friendly. Please approach me, and we can talk more about it. Thank you.